Hello, class. Welcome to homework review number 3. Recording this from my panic room. We had a homework assignment this week that asked for 3 things. First, I wanted you to show me that you could apply what you learned about standardization and z-scores to a real world problem. Many of you have likely at some point in your academic career experienced a curve, and now I wanted you to see how the curve actually comes together, right? How the sausage actually gets made, and really make the point that the curve is, it's not really something you always want. Personally, I mean, there's this idea that the curve always benefits you. Not always, as you would have seen if you got the right answer. Then I wanted you to show me you could do your first hypothesis test, which was a z-test. And then finally, some confidence interval things in stata. So let's get to it. Following table displays a set of exam scores for a statistics course. Maybe it was this one. Maybe not. The professor wants to curve these grades and decides that the new distribution, right, which is what you have to get to, is going to have a mean of 75 points. We want an average score across, the whole class of 75 and a standard deviation of 10. And to do this, we need to follow 4 steps. So you are given a table where columns 1 and 2 were filled out, right? Column 1 is just the students, right? So we have 10. Column 2 is how they performed on an exam. And they are as follows: 44, 85, 21, 38, 74, 62, 68, 83, 90, and 79. And we need to then calculate a z-score and use that to get x new using a formula that was provided for you. So 4 steps here. The first thing we had to do, right, if we want to get to x new, let me just go up to this formula here. It says, let's just point at the screen. X new equals mu new plus z times sigma new. Mu new, right, the new mean, we know that's going to be 75. And sigma new, we know that that is going to be 10. So what we need is z. And in order to calculate z, we needed to get the standard deviation. And in order to get the standard deviation, we needed the mean. So there was a 4-step process here. First, calculate the mean. The mean of this old distribution, 64.4. And using that, we calculated an old standard deviation of 21.78. If you rounded slightly differently, I highly doubt it will be a problem, right? So then, using that, I plugged it into my z-score formula, right? Because now I know what the mean and the standard deviation is. So in column 3, the z-score, the values that you see here are obtained by doing z equals xi minus x bar divided by sigma. Or actually, I should say mu, because we're using a population here. Sorry for the carelessness. So if we take the first student here, who scored a 44, not so good, how many standard deviations away from the old mean is that? Well, 44 minus 64.4 divided by 21.78. Yeah, 21.78. And that gives me a z-score of negative 0.9364. So using that information, right, using that formula and the mean and the standard deviation, I do that 10 times over, right, for all 10 students to get the following z-scores. Then that gets plugged into my x new formula. I have to take that z-score. So again, focusing on student 1, 75 plus negative 0.9364 times 10. So order of operations, I have to do z times sigma new first, and then that is added to or subtracted from, right? Depending if it's subtracted from, if it is a negative value, I do add that to the new mean, which is always going to be 75. And the values we should have ended up with, more or less, are 65.64, 84.46, 55.08, 62.88, 79.41, 73.9, 76.65, 83.54, 86.75, 81.7. So what happened to our distribution? Well, now we have a mean of 75 and a sigma of 10. So how does the mean, standard deviation, and shape of the distribution differ? Well, for the new, it's got a much larger mean. That was the entire point of doing the curve, and it has a tighter standard deviation. The shape, however, is going to be unchanged, right? And that was the benefit of using the z-score. So the distance between the mean, like the z-scores tell us the relative location within the distribution. So we haven't changed the shape, right? The distance between scores is actually still the same, but we have tightened up the standard deviation. Did curving the exam help the students? Mostly yes, but I did want to point out that some students kind of got screwed, right? There was a student that achieved a score of 90 and they got dragged down, right? Some people actually ended up with worse scores. And many people who were kind of around the mean to begin with didn't change all that much. They were average in the old distribution and they remain average in the new distribution. Like, that kind of sounds harsh, but this is really all a curve is. I'm not a huge fan of curves for this reason. For one, I think it's a bit arbitrary. It's like, so this distribution has a mean of 64. What if it didn't? What if I just made it into 75? Okay, well, mathematically, we can do that in the right way without changing the shape of the distribution, and that's all the curve is. But I view it as largely arbitrary. And even though the math is not arbitrary, I think the decision to curve is arbitrary. So for those reasons, I typically do not curve, but anything's possible, I guess. So yeah, did curving the exam help the students? What I really wanted you to point out here was some people are going to be affected differently by this. If you were that student who got a 21 on the original distribution, you are probably pretty happy with how you ended up. I mean, you still did poorly in relation to all your classmates, but there's no doubt that your score rose. But for the students who did very well, now they actually get a grade back that is less than what they actually earned. And I would not be happy about that if I were that student. And so I was hoping for you to point that out, that some people were helped by this, others were not. Okay, now moving on to our hypothesis test. 2010 census population data, well, that might be helpful, tells us that the average American had completed 12 and a half years of schooling, 12.5, with a standard deviation of 1.5 years. We are curious whether this has changed by 2020, so we sample, also important, 150 people, and we find a mean of 13.5, right? 13.5 years of schooling. And we want to know, with 95% confidence, that educational attainment really is different in 2020 as compared to 2010. So complete all your hypothesis testing steps. Step 1, state what you know. I'm going to do this first before I identify the type of test I have to do, because that it's the knowns that lead me to make that decision. So mu is 12.5. That's my population mean. Sigma is 1.5. That's my population standard deviation. X bar, 13.5. It's my sample mean. And N, 150. Notice how I've been given population standard deviation, but I have not been given sample standard deviation. Great. As long as I have the population data to work with. I don't need the standard deviation of the sample, because this will allow me to get a calculation of the standard error. If I lack that, then I have to get the sample standard deviation and use the t-distribution. But we'll get to that in our next homework. So that was step 1. And using what I know there, because I have the population standard deviation, I will do a z-test, specifically a two-tailed z-test. And I will do a two-tailed z-test because I have been asked whether the value in 2020 is different from what the value was in 2010. So when I say different, could go either way, right? Could be greater, or it could be significantly less than. That's a two-tailed test. We split our critical region on both sides of the distribution. So moving to step 2, you could have done this a multitude of ways. H0, I wrote mu equals x bar. H1, I wrote mu does not equal x bar. Right. So the first is that these two values equal one another. The second is that they don't. Right. So I got to make sure I use mu there in my population, work. I could have also written H0 as educational attainment is the same in 2020 as it was in 2010, and then H1 educational attainment is not the same or is different in 2020 as compared to 2010. That would have also received full credit. I could have also written H0 mu equals 12.5 and H1 mu does not equal 12.5. Any one of those three would have gotten full credit. Steps 3 and 4, I'm going to get very good at this. Alpha is 0.05. I know that because I was asked with 95% confidence. So knowing that I got 95% confidence, 1 minus 95%, 1 minus 0.95, that equals 0.05. And so what I do then to find my critical statistic, I will grab that alpha level, divide it in half, and I need to find the z-score that corresponds to 2.5% area beyond the curve. And we get that by looking at column C, or we get that by memorizing this value because it shows up a lot. Plus or minus 1.96. So that is the z-score, where if you look up the z-score in your standard normal table of 1.96 and find what it says in column C of the standard normal table next to a z of 1.96, it will say 0.025, 2.5%. So 2.5% on the left side of the curve and 2.5% on the right side of the curve. If my value that I calculate with my z-test is greater than positive 1.96, or if it is less than negative 1.96, either one of those will allow me to reject the null hypothesis. All right, let's go to the videotape. Here, I will have to do the following formula. Z equals x bar minus mu over sigma x bar. That is the sample mean minus the population mean over my standard error. To get the standard error, right, follow my mouse here, I now have to calculate that using the formula of sigma divided by the square root of n, right? The standard deviation of the population divided by the square root of the sample size. So in our problem here, sigma is 1.5 and n is 150. So that reduces to 1.5 over 12.247, which equals 0.1225. That's my standard error. Follow the arrow and you will see that that gets plopped right in the denominator of my z formula. So z is calculated by taking 13.5 minus 12.5 over 0.1225. That's which again is my standard error. This reduces to 1 over 0.1225. And that is equal to 8.16. So, as I do in class, is 8.16 greater than 1.96? Yes, it is. So this is, with 95% confidence, we reject H0. We reject the null hypothesis and conclude that educational attainment really was different and greater in 2020 as it was in 2010. Hopefully we all got there. If not, happy to provide practice problems. Happy to provide help in office hours. happy to go over any work with you personally if you can't figure out where you might have gone wrong. So that's what we had for the hand calculations. Part 3 was stata, and fairly simple. I just wanted you to pick one interval variable, any interval variable, and get a 90, 95, and 99% confidence interval surrounding it. And what you would see, as we've gone through this a few times now, as confidence increases, the range of the interval, the distance between the lower bound and the upper bound, has to increase, right, to account for a greater possibility of values. As we decline in confidence, we go from 99, 95 to 90, then the confidence interval will very much tighten because we're going to give ourselves more of a chance of making a mistake. So hopefully we all got that. I'll have grades returned to people in fairly short order. Those of you in quarantine, hope you're doing okay out there. Those of you not in quarantine, I hope we keep it that way, and myself included. I don't want to end up in quarantine. Take care of yourselves, and again, if there's any questions or concerns, I hope you will not hesitate to reach out, and I'll do what I can to get you on track, and I'll see to it that you receive help to the degree that you need it. Take care.